We can view a Turing machine as computing function values. If we initialize our Turing machine with blank x on our tape, then we can start in our initial state with our tape, and eventually we may end in the halt state with something in our tape. So if this happens, we can say our Turing machine has computed f of x equal to y. But if our Turing machine crashes, we can say that x was not in the domain of our function. But remember, it's also possible that our Turing machine might run forever. Since that would mean our Turing machine never returns a function value, or does it? That's another question which we'll look at later. We'd like to know if our Turing machine will eventually halt or crash on an input x. And so we might ask, can we make a sanitizer that only passes to the Turing machine inputs that will cause it to halt or crash? Now, for reasons, it will be convenient if we can assign a numerical value to any Turing machine. But how could we do that? Turing's original paper introduced the idea of a description number. His idea was the following. Consider a move like this. We can describe this move as where we have our starting state, we have our symbol red, we have the output symbol, we have the move, and then we have the new state. We could then encode qk as a d followed by k a's, and so that gives us a way of recording the starting and final state, and then ak as a d followed by k c's. And that gives us a way of recording the symbol read and the symbol written. And then our move is just our standard right, left, or stay. For example, suppose a Turing machine has a move like this. We can rewrite this. Our initial state is Q1, and the symbol we read is A2. We print the symbol A1, we move right, and change state to Q3. And so Q1 is going to be a D followed by 1A. A2 is going to be a D followed by 2 C's. A1 is a D followed by 1 C. R stays R. Then Q3 is a D followed by 3 A's. Now, since a Turing machine generally has many moves, these moves are all encoded, and each move will be separated by a semicolon. We can then assign numerals to the letters. For example, we might say A is 1, C is 2, D is 3, and so on. This is actually Turing's original assignments, which turns our description of the Turing machine into a description number for the Turing machine. Now, the exact details of how we find a description number aren't important. The encoding, how we assign the moves, and so on. What is important is that every description number corresponds to a unique Turing machine. Now, because we could list the moves in a different order, each Turing machine will have several different description numbers, but this won't affect the argument that follows. We'll refer to the Turing machine with description number k as vk. For example, suppose we want to find the description number for the Turing machine corresponding to the identity function over the alphabet just consisting of the 0 symbol. So first we'll create our Turing machine. Since this is the identity function, then what we want to do is, given our initial state blank x, we want to eventually derive the Turing machine in the halt state, and the tape head should be just after the end of our input string. So the only thing our Turing machine needs to do is to move to the end of the tape. And we'll assume that our input has been cleaned so it doesn't have any blank squares in the middle, since having to do so would make our Turing machine a lot more complicated. So the moves of our Turing machine should be something like the following. From the initial state, if we read blank, we switch to state Q1 and reprint the blank, move right. And then if we're in state Q1 and read a 0 or blank, we should make the moves. To convert this into a description number, we do need to index our states and symbols. So we'll let our halt state be state Q2. The blank, we'll let that be symbol A0, and the symbol 0, we'll let that be A1. So in our first move, we're in state Q0, we read blank, we print blank, move right, and change to state Q1. And we'll encode that as Q0 is a D followed by no A's. Our blank is the symbol A0, so it's a D followed by no C's. And we print that symbol, so we do that again. Then R is just R, and a Q1 is a D followed by 1A. And our moves will be separated by semicolons. Similarly, our second move, start in state Q1, read a 0, print a 0, move right, and then stay in state Q1. And so that'll be Q1 coded as D followed by 1A, 0, that's symbol A1, so it's coded as a D followed by a C, and again, R is R, and Q1 is DA. And our final state, which will be encoded as and so using Turing's assignments, these letters get converted into the description number. We'll refer to the Turing machine with description number k as phi sub k. And this allows us to define a function whose input is a Turing machine. Let's see where this takes us.